Hello and welcome back. In this installment, we're going to be covering the shorthand form of the sensible heat equation, Q equals 1.08 CFM delta T, something that is near and dear to HVAC engineers across the world. So my goal in this video is to explain where this magic 1.08 comes from and why this is so valuable to us. For those of you who have had a physics course, perhaps in high school or something of this nature, you should have been introduced to something that is typically denoted as Q equals MC delta T, where the heat added or subtracted to some substance or control volume, as we would typically term it in a thermodynamic sense, is equivalent to the mass of that substance multiplied by a specific heat parameter and a resulting temperature difference. So if we apply some level of joules per second, some level of energy, some watts, and we have certain amount of kilograms, we have some parameter that describes what substance you're dealing with. This will be different if you're dealing with water or air or metal. You will get some temperature rise or fall. And this form up here is just a shorthand form for this. But it's well tailored to the HVAC engineer. So let's quickly just set up what is our typical problem as a HVAC engineer. We typically have a zone or a room that is receiving heat from inside or from outdoors, and we need this air to leave this room at a comfortable temperature, say 70 degrees Fahrenheit or around 21, 22 degrees centigrade. And we need to know what is the amount of mass and the temperature of the air that we got to put into this space to absorb all the heat, so that when you add this heat, that it results at this level. So we're typically dealing with moving air, and so we're not dealing with a static mass per se, we're dealing with a mass flow rate in our case, and we also are dealing with only air. And so we're going to rearrange some things and we're going to result in this formula. So an important item to note is for air has a CP of around 0.24 BTU per pound per degree Fahrenheit. And just to prove this to you, I have a sheet here from my textbook, and this is ideal gas specific heats of various common gases at 80 degrees Fahrenheit. If I look at air, I can circle this here. This is the sensible heat, specific heat for dry air. Now, we'll also be needing steam, because we typically think of air as dry air only if it doesn't contain any H2O molecules, but we know that there are some H2O, and when we deal with that, we are talking about moist air, and I've described this in some of my psychrometric videos. So the other specific heat of interest is this for steam. So if I go back to the top here, and I look at what air is, and I look at the Q equals MC delta T, well, I can add these energies together, and so I'm going to have the mass of air times the CP of the air times the delta T of that air plus the mass of the vapor, CP of the vapor, and that times its same. We're assuming these temperature differences are the same. Now, we can divide everything by some unit of time, and we can make these all per unit time. So this will be now in power or watts, and this will be in, for instance, we'll say pounds per hour, and this would be pounds per hour, but it really doesn't matter much. And we have this total sensible heat equation. Now, if we're in the United States, when things are designed for air conditioning systems, they are always in CFM for air, and they are in degrees Fahrenheit for air. These are our two major units that we will be using, and so we don't really care much about this exact mass. We don't deal with pound mass per hour or pound mass per second, something like this. The unit that is specified is actually a volumetric flow rate. It's a volume over a time. And if we wanted to get mass, we just need to basically use the density, where we have mass divided by volume, and that is density. So while this formula here is exact, we need something that is only going to have two items. And this is a volumetric flow rate of just the dry air, because water moisture can be condensed out, and we typically do everything on a per unit dry air mass basis and degrees Fahrenheit. So let's do some filling in. We have Q is equal to the mass flow rate of air. We now know that this term is 0.24 BTUs per pound degree F multiplied by a delta T that's also in degrees F, plus the mass flow rate of vapor times 0.445 BTU. So again, water is has a much higher specific heat than just air by itself, which again is nitrogen and oxygen and items like this, also multiplied by our delta T in degrees F. Now, an important thing is that we typically don't want to have to deal with two mass flow rates. So what we do is we take advantage, we say we have to make an assumption here. Under typical AC processes, we know that this ratio between the flow rate of vapor and the mass flow rate of air, we know that that ratio is around 0.01. And so what we can do is we can replace this m dot v with 0.01 times m dot of the air. So let me go ahead and rewrite that. We have Q dot is m dot A times 0.24 BTU per pound degree F multiplied by your delta T, your change in temperature, multiplied. So this m dot V now got changed into 0.1 m dot A, and we're going to multiply that by our 0.445 BTU per pound degree F, poor handwriting, delta T degree F. And now we can start combining terms here. So let's combine everything that we can. We have m dot A, we have delta T in degrees Fahrenheit, and that's going to be multiplied over here by 0.24. And we also have, so we've pulled out this term, pulled out that term. We need these two multiplied by each other, and if you do that multiplication, you get 0.0045. And so you notice that after you take into account that there's much less mass of vapor in the air, that it actually doesn't make a huge difference on your specific heat of the total of the two components. And these terms are in BTU per pound per degree F. We're now closing in. So in many cases, people will just neglect this portion from the water vapor. And so we can be left with 0.024 BTU per pound degree F. So if we do this, we end up with something like this. Now, again, I said earlier, we typically don't deal in mass flow rate, we deal with volumetric flow rate. And so to do this conversion, we need density. So typically we wanted this flow in units of BTU per hour. So to make this all balance out, that would have meant that this pound per hour would be the units for this mass flow rate. So we need to go from pounds per hour to CFM, or cubic feet per minute. So how do we do that? So if we want to go from a mass flow rate of air in pounds per hour, to get to CFM, we're going to have to multiply it by some things. And the first thing is by this factor of density. Actually, let me erase this here for a second. We need to get to pounds per hour, starting, because we need to replace this pounds per hour, starting from cubic feet per minute. So if we do this, what we'll need is a ratio to get it to hour. So we have 60 minutes in 1 hour. And then we also need this factor of density to go from volume to mass. And what we typically assume is that we're at standard air conditions, and we just assume a density that makes sense, and that will be around 1 pound per 13.3 cubic feet, or feet cubed of volume. And if you do this math, this comes out to around 4.5 times this here, which we typically abbreviate as CFM. So now we can replace a mass flow rate in pounds per hour, this by 4.5 CFM. So into the home stretch, our final form here is our Q in BTU per hour. And remember, this is all for us in America, and other places there are other shorthand forms. But this is equal to, we're going to replace this M dot A with 4.5 times the CFM multiplied by 0.24 BTU per pound degree F. This 4.5 has these units here of minute, pound, hour, foot cubed. But if you believe me, this will all cancel, and you will end up getting, if you take 4.5 times 0.24, you will get the magic 1.08 CFM delta T. And that's it. So the main takeaways from this are that for us in HVAC, for using this shorthand formula, its inherent assumptions are that we essentially neglected, or even included, it doesn't make too much difference, the water vapor of the air and its specific heat content, and also that we're dealing with air that has a certain density of 13.3 feet cubed per pound, or standard air conditions. And so this formula ends up being very useful for us because CFM is our most common unit for dealing with airflow, and we can do many things with this formula in terms of energy calculations for HVAC. And so I hope to see you in the next video.